Hello, thank you very much for joining us for this new online lecture on artificial intelligence. My name is Martial Guérin, and I work at the Scientific and Academic Cooperation Office of the French Embassy in Israel. After our first meeting last week, I'm very happy to keep going on our series of panel discussions that explore the current issues and challenges raised by the development of artificial intelligence. Robots and artificial intelligence have been the subject of movie, books, or comics for many years. Already in 1968, Kubrick depicted in his movie 2001: A Space Odyssey a supercomputer, omnipresent and omniscient, who behaves and thinks like a human being. Autonomous cars, facial recognitions on our phones, intelligent virtual assistants. Nowadays, our daily lives looks more and more like a science fiction movie. Some people even imagine a world where we would be subjected to machines. But could this really happen? To answer this question, it's my great honor to welcome tonight Bertrand Braunschweig. Bertrand, you are an NCA engineer, PhD from Paris Dauphine University. You are president of the Artificial Intelligence, French Association of Artificial Intelligence, for 4 years. You then held the position of director of INRIA Research Center, first in Rennes and then in Saclay. In 2016, you coordinated the preparations of INRIA's White Book on Artificial Intelligence. And since December 2018, you are the coordinator of the research component of France's AA plan. You will tonight explain us what is possible to do with AI nowadays and what still comes under science fiction. For your information, Bertrand will speak for about 40-50 minutes, and he will then answer your questions. So if you have a question, please use the Q&A button and write your question down. I'll be here to moderate the session of questions and answers. Dear Bertrand, thanks again for being with us tonight, and the floor is now yours.
Thank you, Martial, and hello to all. It's also a pleasure for me to talk about the realities and myths of AI. So I will do it like this. I will first give you a very short history of AI, then talk about the recent achievements, which are really impressive, one can say. Then talk about the realities and myths. And if we have time, depending on, because we said we will have 40 to 50 minutes, if we have time, I will say a few words about AI in the society, especially because today, a bit earlier today, was the kickoff of an initiative called the Global Partnership on Artificial Intelligence with 15 countries involved. And if I have time, I will talk about that. So first, a bit of history of AI. In fact, it dates from the last century, even from before the 56. In the 40s, we had the formal neuron, which was defined by McCulloch and Pitts. We had robots, which appeared in the literature, and people starting to fantasize about robots. But also we had Alan Turing, who lived in that period, who really established the basis of AI. With the Dartmouth Conference in 1956, the definition of AI was given. And so from then, in the 60s, people worked a lot on many things, including problem solving, natural language. At that time, people said that the question of natural language translation would be solved by the end of the 60s, at the same time as men went to the moon, and this was not the case, as you know. Worked on games, etc. So a lot of things. Okay, and Martial also mentioned the movie. So, but in the end of the 60s, the book by Minsky and Papert, Perceptron, stopped really the research on neural networks because of limitations for neural networks that were identified. I'm not going to give details, but let's say that they were, at that time, neural networks were not able to model nonlinear behavior, which is really a problem because most of the behaviors in the world are nonlinear. So also there was a report by a British deputy, British Parliament, and scientists. And we had the first winter of AI in the 70s with these reports and books saying that finally AI did not deliver. But then in the 80s, people worked on expert systems, and there was a lot of enthusiasm about knowledge-based modeling, knowledge-based reasoning at that time, knowledge-based systems. But at the same time, in the 80s was the first time when a game was solved by an AI system. That was Chinook, which completely solved the game of checkers. So this means that the system is, when the system starts a game, it knows that it's going to win. It's sure to win. Still, expert systems had many problems, let's say, of consistency of knowledge base, of going up to scale, of connecting with the real world, of divergence of opinions of experts, and many problems. So in the 90s, we had the second AI winter. So investments went down again. But in the same time, we had big successes like Deep Blue that IBM developed, which won against the chess masters. And also, what is very interesting, it's in the 90s that the first convolutional networks were developed, namely by Yann Lequin and other colleagues. And these are the neural networks that people are using now, in fact. So they were developed in the 90s. Big changes appeared around the beginning of this century with the advent of the web. So the web was already existing before, but it really started to develop at the beginning of this century. With wide development, and then all the algorithms, all the methods, all the technologies that people had developed in AI for many problems found an application domain, the web, which has big economic interests, which has a lot of data available, which has a lot of social application. And so that was really the kickoff of the boom of AI, as I can say, from the beginning of the century. And if you look at this, you can notice that the main leaders worldwide in AI are web operators, such as the GAFA, Google, Amazon, Facebook, etc., or the BATX in China. Then in the 2010, we had the advent of machine learning and especially of deep learning. So deep learning has invaded a lot of applications, and for good reasons, because it's behaving quite well. And I will talk, of course, a bit more about that later. So let's say the last 10 years were really the period of deep learning, starting really in 2012, and I will be more precise a bit later. And then what happens now? Well, it's not yet a third winter. We already had 2 winters of AI, but we might have a third winter if we don't behave properly. And I will talk about this at the end of my presentation. But for the moment, maybe it's spring or summer of AI. It's still growing a lot. So we will see if we go back to winter or not. Among the recent achievements, let's say some examples. IBM Watson was the first computer to win Jeopardy. Jeopardy is a game where you have to understand natural language and very quickly answer questions about anything. And so this was done with natural language processing, web mining, very fast web mining, scoring and rating the possible solutions, and all this in 3 seconds using high-performance computing, because the human players also take less than 3 seconds. So that was a big success. There was no machine learning, no deep learning in the beginning in Watson. Since then, IBM added some machine learning in Watson. And since then also, Watson has become a very important product for IBM. They have tried to develop it for the health domain, but also for banking, insurance, and many other applications. Deep learning won in 2012 over the reference algorithms in image recognition, which is ImageNet campaign. That is really a big thing, because from that, everyone in image processing and image recognition and in other domains started to use deep learning instead of, let's say, their traditional tools. A nice achievement also is the one of DeepMind, of Google DeepMind. Well, DeepMind was not Google in the beginning, they were bought by Google afterwards. They first worked on solving Atari games. Well, Atari is a computer from the 80s. Probably many of the people who are around this virtual room don't know what is an Atari. It's a small and nice computer with graphic facilities, and there were lots of games on the Atari. And so DeepMind, they just took the pixels as an input, so 640 times 480 pixels. And from that, learn to react like going left, going right, or shoot, whatever the game needs. And they learned with the reinforcement learning from that, and they won against the 7 Atari games, like Bricks or and many Pong and many other games. And after that, they worked on 30 or something games, and they won all these games. So it was really quite impressive. It's well known that they also beat the world champion in Go in 2016 and 2017, despite many efforts by the Go community with machines or without machines to do better. But that was also known as a big success, using deep learning and reinforcement learning. Deep learning meaning playing with lots of data from past games, and using this data to learn the moves, and reinforcement learning, meaning playing against oneself and becoming better and better and better. The first version of AlphaGo was using a lot of deep learning and a lot of pass game. The second version of AlphaGo, AlphaZero, was only playing against itself and getting better until it became world champion. So a nice achievement. So this is the error rate in image recognition historically until 2016. So now it's even better. So you can see in the first years of this decade, there was still computer vision algorithms, and they were beaten by deep learning in 2012. So the error rate went down to 15% as opposed to 25% before, and now it's below 5% for typical image recognition campaigns. So it's even better than human performance in some cases. Huh? So it's very efficient. Other achievements, such as the language translation, natural language translation. So the first ones to do that were Microsoft with the Skype translator. But now you can find real-time language translation using neural networks and statistical learning with Google Translation, but also Pilot and many applications. You have the personal assistants, of course, which understand, well, which process what you say quite well, like Siri, Cortana, Alexa, and others. So they do speech recognition. They do some reasoning, not much, but they are able to use what they get from your speech to look into databases and give you answers. In terms of robots, so there has been also a lot of progress. Now, I have to say, if you go to YouTube and you look for DARPA Rescue Challenge for robots, you will find a lot of problems. You will see robots falling, not achieving, etc. It's true. But you will also notice so much big achievements. So robots able to drive, to walk in very complex environments, to operate valves, to walk upstairs. So this has been also a big progress for robots in the past, even though it's always nice and funny to look at when they don't succeed. I want to say also a few words about Google Knowledge Graph, which is using semantics to produce structured results. Probably most of you around this virtual room think that they haven't ever used Google Knowledge Graph, and in fact, you have used it. All of you use Google Knowledge Graph if you have used Google for searching. And here I just show what I do with looking for Institut français d'Israël. And you can see the result of a Google request on this topic, which on the left part, you have the typical PageRank response from Google with the most popular pages, etc. So that's normal Google. And on the right here, you have something which looks like being taken from a database because it has some pictures, it has some data like an address, opening hours, phone number, etc., director. In fact, this comes from the Google Knowledge Graph, which is a very, very big graph linking many, many facts being expressed as triplets, let's say object, attribute, value, such as Institut français d'Israël, address, and this is the address. And all these are linked together. So the different elements in this graph linked to one another. And so it's very powerful. This is technology from the semantic web. They have billions of triplets stored in the Google Knowledge Graph, and they use it for this kind of answer. So you can try it with people, with places, with museums, or factories, or whatever, with companies. So if you try it for me, it won't work because I'm not so known by Google Knowledge Graph, but it's not a problem for me. So a few other achievements. For example, Facebook was very, very proud to talk about their personal assistant using AI and machine learning to execute tasks and describe images. So this is an old link, but it's nice because it's a link. If you look at the Zuck in the middle of the link, it shows that it's Michael Zuckerberg himself who is, let's say, involved in these activities. Huh? Mark Zuckerberg, sorry, I said Michael. So, and this is useful for blind people or who cannot see images, and you have assistants that are able to look at images and describe the images for them. I'm not going to talk too much about these other examples. I want to talk about the last one because it's made in Israel. I think it's even made in Tel Aviv by IBM Israel. So it's a very nice achievement because this system can make structured argumentation discussing with human experts. So you take any subject and you want to debate about it, you get a professional debater, which is expressing arguments, and the IBM project debater can do counter arguments in a very structured way. It's quite interesting. So you can find examples on YouTube also if you want to look at it. And it's a mix of technology. So it's based on Watson, but with many additions. So let me show you a few videos of examples of what AI can do today. Here I'm taking a conference from the authors of YOLO. YOLO is a system developed by University of Washington, Facebook, and Allen AI, which is an AI institute. It's used by many companies and individuals around the world. So you can look at
why speed is so important in this domain. Here's an example of an object detector that takes 2 seconds to process an image. So this is 10 times faster than the 20 seconds per image detector. And you can see that by the time it makes predictions, the entire state of the world has changed. And this wouldn't be very useful for an application. If we speed this up by another factor of 10, this is a detector running at 5 frames per second. This is a lot better. But for example, if there's any significant movement, I wouldn't want a system like this driving my car. This is our detection system running in real time on my laptop. So it smoothly tracks me as I move around the frame, and it's robust to a wide variety of changes in size, pose, forward, backward. This is great. This is what we really need if we're going to build systems on top of computer vision.
I'm going a little further in this example, just to show
80 different classes in Microsoft's COCO dataset. It has all sorts of things like spoon and fork, bowl, common objects like that. It has a variety of more exotic things, animals, cars, zebras, giraffes. And now we're going to do something fun. We're just going to go out into the audience and see what kind of things we can detect. Does anyone want a stuffed animal? There's some teddy bears out there. And we can turn down our threshold for detection a little bit so we can find more of you guys out in the audience. Let's see if we can get these stop signs. We find some backpacks. Let's just zoom in a little bit. And this is great. And all of the processing is happening in real time on the laptop.
Okay, so you see that it's quite powerful. In fact, it's 2 years old, this video. So now they do much better, and especially if you look at what is provided to cars in terms of recognition of people, other vehicles, etc. They can now not only identify, but they can also draw a very complex line around the object in order to show that they really understand how the object is moving. So that's another example from an INRIA research team, from the top research team in Grenoble, south of France. But it's much more difficult. It's not recognizing objects, it's recognizing actions. So you see that people are walking, more or less what they do in this movie. They walk and they talk together and they sit. So this is, but in order to be able to recognize actions in movies, it's much more difficult. It demands much more computing power, but also complementary information in order to do that, additional information. So this is also a few years old, but still recognizing actions in videos is very, very complicated. And of course, it's quite important for people who want to monitor what is going on, for example, in a stadium, in a street, etc. I like also this example, which is an example from Google. It's Makoto Koike, who is the young guy behind the two others. So his parents grow cucumbers. They are Japanese cucumbers growers. And what they said to their son is to develop us a system which is able to classify the cucumbers. In fact, they have 9 categories of cucumbers. I think I'm going to stop the video if I can here. Yeah, they have 9 categories of cucumbers because they sell for different prices. If they are really nice, if they are curved or they are straight, or 9 categories. So they are taking a picture of the cucumber from on a very, very small computer, on an Arduino Micro, which is a computer which costs something like $20. processing it through a Raspberry Pi, which is another $20, sending the machine learning data through Google Cloud, which is doing the classification. And in the end, it's saying, this is a cucumber of category 9 or 8 or 7 or whatever. And then it puts them in the right basket. Now, if you think about it, it's very nice. And it has 70% success rate, which means that Mrs. Koike only has 30% of work left to look at what has not been classified correctly. But think about this, the question of artificial intelligence. The machine is doing very well a very specialized job, which is to classify the cucumbers, but it doesn't know what is a cucumber. It does not know that it lives in three dimensions. It only knows 2 dimensions. It doesn't know that it can be eaten. It doesn't know that it grows from a small cornichon to a big cucumber, etc. It doesn't know that it has a taste. It just knows how to recognize green objects on a gray background. So it's very useful, it's very powerful, it's very specialized. And so it makes you think about what AI can do. AI can do this very well. But if you ask this machine, what is the next movie that you would like to see in your home, there's no chance that it will be able to do anything. For example, or some other examples. What time is it? Yes, let's spend also some time looking at this one. This is reinforcement learning. Okay. Reinforcement learning of a paper robot, so trying to play Bill Bokeh. And so it learns from its successes and mistakes. Huh? So this is accelerated. So the robot has now had 20 trials of the same exercise. So let's look at it. Huh? It's not progressing that much in the beginning. Not yet. Very little hope, maybe. Let's see. Yeah. So this machine should be able to learn something in the end, no? At least it touched the curve now. After 8 trials. Not so bad, huh? Almost done. And after 100 trials, you can guess what happens. Success, very good. Okay, it's not the most difficult Bill Bokeh of the world, but still it works. And then once the machine has learned how to do it, then I don't know if you try to do this, but 10 times in a row, where I am not able to do it, but the robot now is able to do it without any problem, because it has learned very precisely how to do the job. So reinforcement learning from errors and successes. So what can we do with that? We can do many things. We can improve health, such as X-ray interpretation. So this is an example from neural networks, 121 layers deep network, detecting pneumonia from radiograph, trained with 100,000 images and more accurate than a professional radiologist. So very useful for helping radiologists in processing the data. This is another example. I will stop the music quickly. To stop it. Sorry. Okay. Yes. So this is in French story. So an AI system created a new song from the Beatles. In fact, it's between the Beatles and Beach Boys. So it learned from a lot of musical extracts, and now is able to create new music. And this was done by François Pachet, a French researcher who is now head of Spotify research. Huh? So this is from 2 years ago, and since then they did even full records created by AI systems. Huh? So very nice music, if you like it. Other example taken from the news. So you have to take this with some kind of precaution. If you're not familiar with the automotive, with the self-driving cars, autonomous cars, there are 6 levels of autonomy. I will come back to this later. So here Magna says, okay, they are able to go to level 5, which is the top level on public roads. So with many kilometers run. Israel is one of the big countries for autonomous cars, because of the first company which was born in Israel, which was really the leader of image recognition for cars from a few years ago. Huh? So it will help us to drive cars, which is nice. Okay, it beats the best world players in game. We have talked to examples of chess, examples of checkers, or Go. And the last achievement by DeepMind was to beat the pros at StarCraft. Okay, I'm not an expert in StarCraft, but I know that it's much more difficult than the other games. Huh? So also they are able to do that. It can also power autonomous weapons. So I encourage you to go to YouTube and to look for this video, Slaughterbots, which is probably not the typical way that you would think of an autonomous weapon. Look at it, it's very small, it fits in your hand. It has cameras, a face recognition system, explosives, and it's able to do a lot of harm. So look at the video and you will learn about what can be done with this kind of technology. You see the number of students killed, that's of course a fiction. Huh? But still people are working on that. Huh? So that's another big domain for AI. Generally speaking, many other applications such as recommending videos for banking and finance, attribute loans, design and investment. On cybersecurity, many applications, help the blind people, as I already said, customize an advertisement, etc. Many applications. Okay, this was really the recent achievements. I will talk about the realities and the myths now. Okay, we have seen that before. So image recognition, we know that it's quite good, better than human performance on some specialized tasks, as we already seen. I don't need to tell it again. In videos, it's much more difficult. So here's another example taken from the same Imonia research team, where you see identification such as walk, sit down, and other activities. However, it's very limited possibility for the moment. It's a lot of research. And let's say it only works in, let's say, very configured conditions in small domains. You cannot have activity recognition in general. And I will go back to this even a bit later. Image annotation, it can do well. For example, this is here taken from CaptionBot, which is a bot done by Microsoft, with some AI recognition in it. And you can see the description here. I think it's a group of people riding skis on a snowy mountain, and they seem rather happy, which is really a good description of the image. So I would say, let's congratulate CaptionBot for this achievement, which is very useful. Huh? But it doesn't work in all kinds, in all cases. In this case, the situation understanding doesn't work. So you see that the system here says a group of people riding skis on a snowy surface, and they seem, I don't know exactly how. Of course, this is not the case, so some progress still needs to be made. So.
En quelle année est né le général de Gaulle?
I want to stop this one.
Est né le général.
I need to do some explanation first. In fact, and I apologize, this is in French, so I will translate. So processing speech is very successful. You can go to your favorite Alexa, Siri, or whatever and talk to this system, and it will more or less process your sentence in an appropriate manner. But look at this example, which is more how these machines understand what is going on. I'm not talking about processing, I'm talking about understanding. So the Siri says, I'm listening to you, Bertrand. Bertrand, it's me.
En quelle année est né le général de Gaulle?
So when was the Général de Gaulle born?
Charles de Gaulle est né le samedi 22 novembre 1890.
Very good, you go to Wikipedia and you take the answer, not a problem.
En quelle année est-il mort? En quelle année est né le général de Gaulle?
I have to go back there.
En quelle année est né le général de Gaulle?
Charles de Gaulle est né le samedi 22 novembre 1890.
En quelle année est-il mort?
Nous sommes samedi 9 février 2019.
So now the question is, when was he dead? When did he die? And the machine answers completely wrong, and just gives today's date, which is not what you expect. The problem is the he. When did he die? Because there's no context, so the machine doesn't understand that I'm still talking about the same person. So I'm trying to help.
En quelle année est mort le général de Gaulle?
When did Général de Gaulle die?
Charles de Gaulle est décédé le 9 novembre 1970 à l'âge de 79 ans à Colombelles-les-Deux-Églises.
Est-ce qu'il est encore vivant?
Is he still alive?
Bonne question. Bertrand.
No answer. No
Est-ce
answer.
que le général de Gaulle est encore vivant?
Voici le résultat de ma recherche sur Internet pour est-ce que le général de Gaulle est encore vivant.
So some explanation is needed here. You see that the machine lacks context. Huh? When you say he doesn't understand, so you have to say who you're talking about. And then when you say is he still alive, even though the machine has the information that he was born on a certain date and died on a certain date, the notion of being alive is unknown to this machine. So no way to process it correctly. So no real understanding, just processing speech correctly, but we need to make a lot of progress on understanding language in general.
Okay.
Learning correlations. So all these deep neural networks, they can do many things. So they can learn correlations between images and the expected output. So the classification here is you give an image and you say correctly it is a cat or a dog, whatever. So it's learning to relate the set of pixels on the left to a class on the right. But in fact, it's learning correlation between these data and not causality. For example, here you have an example of spurious relation. You are able from this graph, from this data, to predict the number of drivers killed in collision with railway trains from the crude oil imports from Norway. Of course, there's no causality here. It's just that the curves are really similar, so you can predict one from the other. If I give you the number of drivers killed in collision with a train, then you can tell what will be the US crude oil import from Norway next year. But there's no, of course, you understand that there's no causality. Or as far as I know, there's no causality. So learning causality, all these systems, they are learning correlations between the data and not learning causality. Learning causality is much more difficult. It's a research problem. And some people are working on it, but for the moment, the results are yet to be obtained. Learning from millions of examples, all these deep learning systems, they learn with huge amounts of data. Millions or hundreds of millions of images or voices and recordings or whatever. And so they do it like this, they do very well, but they need millions of examples. And this costs a lot, as I will show a bit later. Learning from a few examples, this is a scene taken from an INRIA research team in Bordeaux called Flowers, where they are trying to do what they are doing what they call developmental robotics, which means teaching robots to behave by interacting with humans. So it's more a question of artificial curiosity, how a robot can behave in order to learn with not so many examples. And so this is much more difficult, but it is how we humans learn. If you take a baby and show him or her a cat or 2 or 3 cats, then he or she has understood what is a cat. It doesn't need millions of examples. Huh? And this is what people are trying to do. So learning with really few examples, we are just on the beginning of this kind of research, I would say. Autonomous driving at the moment, so there are 6 levels from not autonomous at all and no active assistance system to level 5, which is fully autonomous, which means that you can sleep in the car, you tell the car where to go, and then the car will take you there. So at the moment, depending on the companies, on the advertisements, etc., we can say that we are between level 2 and level 3. Level 2 is really traffic control, so you're braking when there's someone in front of you or accelerating when there's a dangerous object behind you, but maybe not changing line. Here, awareness for takeover at level 3, the machine is more or less able to change line and to take over. So not so many cars are able to do that at the moment, and we have to be very careful. Maybe just on autobahn, on highways, and even I would not be completely confident with that. Huh? And now going to level 5, fully automated, no driver. We at INRIA, we published a book a white book on autonomous driving, and we say it won't be before 2040. So still 20 years to get it. Some people say that it's going to be before, but I don't believe them. And level 4 is even more difficult. Level 4 is needs the driver to recover when the machine is not able to behave correctly, and this needs a lot of attention because the driver will not be always awake and ready to take over if the machine has a problem. So big debates about that. Other facts and myths about AI. So some things like expert reasoning in small words is really feasible. So you can write rules. So this is, let's say, more traditional AI with rules and knowledge management. So rules like that, if the customer is such category and he has bought this and that, then you apply a 5% discount and you can change the rules and then calculate the price. These things that we can do easily with rules, it works well. So expert reasoning in small world is more or less a solved problem. Many of our information systems use things like that. But doing common sense reasoning, such as this one, so the question is whether John Smith has a degree or not. Well, we know that John Smith is an engineer, that's his occupation. So then it means that he has learned and got a diploma from a university, he has been in education, and he has got a degree. This is really a common sense reasoning that we all do, but in order to put it in a machine is very, very difficult. So once again, there has been a lot of attempts to do common sense reasoning, but for the moment, it's not convincing. Okay, you take the Google Home and Amazon Echo and Alexa. They are very good at doing some specialized processing. In fact, they do it very well. They process what you say, they process your speech, and they convert it to requests that they put into databases or services that they find on the web, and then they can answer. They do it quite well. So it's very specialized. The only thing that they do well is process what you say. But they don't reason about the world, etc. They don't do anything like that. They just then get answers from computer services, I would say. But strong and general AI, such as the HAL from 2001, The Space Odyssey on the left, or this robot taken from the famous French cartoon Blake and Mortimer, where Professor Sato says, record, follow the bad guy and destroy him. So in order to be able to do that, you need to be able to make plans, to move, to recognize your environment, to understand the context, and then to modify your plans. So it's very, very complicated. So at the moment, general AI is still far from us. So all these systems are very good at proposing decisions from data. This is what we have seen in many examples. But another big question is, are they able to explain the proposed decisions? And so if you are using neural networks, deep learning networks, deep learning systems for, let's say, giving loans or not, I put you in the situation where you are the customer and you ask to your bank's chatbot, was my loan accepted? And the bank's chatbot says, no. Too bad. But can you tell me why my loan was not accepted? And the chatbot says, no, I can't. But why can't you tell me why my loan was not accepted? Because I'm an artificial intelligence system which has learned from data and I'm not able to produce any explanation, which is not fine. Huh? Okay, so but can you prove that your decision is correct? No, because we are not in position to prove the outcome of a machine learning system with deep learning. It's not possible yet. Okay, but have you been certified by some authority for making this decision? No, there's no possible certification for deep learning system at the moment. So what are you going to do? You're going to cross the street and go to another bank. Huh? So this is really a big question at the moment. It's we can call it transparency of AI system, explainability, and more generally, trust. And trust is really the big matter for AI. We want to establish AI which is trustworthy, and for the moment, it's not yet the case. And so this is a big subject. If people like you and me don't have trust in the AI system, then we will just reject them, and then it will be the third winter of AI. So we have to work on trust, which is a big, big problem at the moment. And I would just like to conclude in the next 10 minutes by showing you a few highlights from a document which is called AI Index. AI Index is produced by the AI people in Stanford in California, and they are looking each year at the progress of AI. So this year it has been a big document of 160 pages with lots of data, and I will just highlight a few of these data, so for you to see where we are now. And I see that Martial is going to tell me that I have 10 minutes left, and it's fine. It's fine. So, yes, if you look at, let's say, general development of AI is exploding. You can see the numbers of AI papers published on arXiv, for example, in the last 10 years. So it's really exploding with essentially machine learning and neural networks and pattern recognition being the reason for the explosion of numbers of papers about AI. So this is well known, no question. This is another very interesting data. It's the activity recognition best or easiest activity recognition that have been identified. And you look at the precision which is shown here, it can go to, let's say, 80–90% in the case of riding bumper cars or dancing Zumba. Not too difficult to recognize someone dancing Zumba or playing accordion, a bit more difficult to do rock climbing, etc. But okay, on these ones, which are the easiest, you still have in some cases 20% of errors. So someone is playing accordion and you don't know that he's playing accordion, maybe you classify it as something else. Now, if you look at the most difficult one, the hardest activity, and I don't know, frankly, I don't know why drinking coffee is the most difficult, but there's only a 7% success rate, meaning that in 93%, the activity of drinking coffee is not recognized by the best AI system for the moment. And same with the other examples, such as playing rock, paper, scissors, or gargling mouthwash, whatever, which is nice, or shot put, or whatever. So, so there's a lot of progress, as I already said, to be done on activity recognition. At the moment, the systems are not really able to do it. If I look at general language understanding, there's something called GLUE, which is General Language Understanding Evaluation here, which has a very, very impressive performance rate, because in the last 2 years, it went from 75% success to over 87%, which is what they qualify as human performance and even better. So in terms of being able to answer questions in natural language and help and having discussions with humans, faking understanding what is going on, has really made a lot of progress. Well, despite what I was saying in the previous document, and even though from that they invented a second test called SuperGLUE, which is even more difficult and on which they are progressing quite well. Okay, another example which is developing a lot is the autonomous militarity systems developed worldwide. So you see in the last 10 years that we now have much more autonomous weapons research for combating, for targeting, and for other purposes. So it's growing, despite whatever you can think of it. And I want to finish. I think I will finish with this one. It's a bit more difficult, but it's very, very important. This one is showing the computing need from the most sophisticated AI system along a period of 60 years. So from the 60s, well, not little data, of course, until now. And you can see that the scale is logarithmic. So it goes from -10⁻12 to 10 to 1,000. And this is the number of petaflops. So what happened from the 80s till, let's say, 10 years ago, is that the growth of the computing need by the typical AI, the most sophisticated AI system, was following Moore's law. Moore's law says it doubles every 18 or months or every 2 years, depending on how you count things. So this is for all of computer science, it's normal. But since the last 10 years, now it doubles every 3.5 months. 3.5 months, yes. So this means that it multiplies by 1,000 in 3 years. And so the global need for the most sophisticated system here is really impressive. It uses probably, it's a number of zeta operation, zeta operation. Zeta is 10 to the power 21, and I think it's 170 zeta operation for the most sophisticated system, which happens to be AlphaGo, the one that won at Go with reinforcement learning. And so it uses a lot of computing power and also costs a lot of energy. Moreover, recently, in the beginning of this year, Google presented his last chatbot, Mina, in this article towards a human-like open domain chatbot. Very nice chatbot, which is able to talk about more or less anything. So it's a general chatbot or general language chatbot. So you see examples of conversation here between a human and Mina. So it looks quite good. I don't need to tell you detail. You can look at the paper. And so it's nice. It's nice. Although, as I said previously, it doesn't really understand what it's doing, but it's able to talk about many things. But the paper says we trained our best model for 30 days on a TPU with 2048 TPU cores on the Mina dataset. Okay, a TPU is something like, which is 10 times more powerful than the GPU, which is the best, almost the best system that we can have for machine learning at the moment. So 2000 TPU is really a huge amount of processing power, and it runs for 30 days. So this means probably it has used something like 3 million kilowatt hours to be trained in order to have, let's say, normal conversation with a human operator. So we are really hitting the planet in order to develop these systems. And we cannot go on like this, and moreover, if it continues to double every 3.5 months, we are going to reach a limit. So we have to care about the energy demand of AI in general. This typically has a number of parameters in the billions, and recently OpenAI, which is another institute, published a paper about a system which has 170 billion parameters, which probably needs even more calculation. And so we really have to think about how AI is developing, how machine learning is developing in order not to heat our planet for, let's say, these kind of reasons. Okay, the hot topics at the moment, and I will really finish with that, as we said 50 minutes. I didn't talk at all about some of them, so it's going to be new for you. The hot topics are to distribute learning on the network in order, let's say, to respect privacy and the confidentiality question. So people call that federated machine learning or edge computing on the Internet of Things. And I said this one, AI methods that need less resources, so less energy, less memory, less communication. And so we think that we can probably do that with AI methods which are called hybrid, so combining machine learning and other paradigms, other methodologies, such as knowledge processing and also numerical simulation. The idea is that machine learning is really learning without any knowledge at all. And if we can combine it with knowledge that we have about the world, either by formal knowledge or by knowledge done embedded in numerical models, then we will be better. So hybrid in AI is also a big topic at the moment. As I said, verifying or certifying trust, explainability, and interoperability, that's quite important. Okay, and the rest, I'm not going to talk about this one, but also the last one, detecting and resisting to adversarial attacks. Okay, I haven't talked about adversarial attacks. I think, if I remember well, I think that Benoît Leblanc has probably talked about them last week. So let's say that adversarial attacks mean that you are very sensitive to noise in the data, and the noise can be organized so that you do wrong classification with some kind of noise that has been arranged for this purpose. So being able to detect and resist to that is really important. So I'm not going to talk about AI and society. I leave it for another time, maybe another conference, whatever. And I stop here and I will wait for your questions. Sorry, I stop. Tell me where I stop, or maybe I should just stop presenting. You tell me, Martial.
Yeah, you can take off the screen now and we will put it at the end again.
Okay.
So let's start my video. Okay, thank you very much, Bertrand. It was very, very interesting. And we do have some questions. So if you have questions, don't hesitate to use the Q&A question button, and we'll try to take all of them. So let's start with the first one. So it's a general question. I'm reading you the question. So neural networks, which are leading much of AI application, is non-interpretable and non-transparent, raising issues of bias, fairness, and the basis of their decisions. Do you think government should legislate which algorithm should be used for AI? And if AI researcher, like the person who is asking, cannot explain how their neural networks work, should law exist that limit their use?
Very nice question. Thank you. In fact, we are discussing this a lot at the moment. As I said in my introduction, we are just launching the Global Partnership on Artificial Intelligence. The kickoff has been just 2 hours ago with 200 people attending on the network. And so these are the kind of things that we discuss. It's also something that the European Commission is looking at. So the European Union has published a white paper on AI back in February, and it's waiting for comments from the different stakeholders about this question of regulating AI or not. So we say we want to do AI for good, so we want to apply principles. So a lot of people are working on principles on AI. Let's say you can take the Montreal principles, you can take the OECD principles, you can take the UNESCO principles. They more or less all look the same. It's about fairness, transparency, etc., responsibility. But this technology is still not in its infancy, but it's still not fully understood. We don't fully understand the mathematics of the neural network. We are not able to predict a number of things. So it's a bit early to regulate. We can suggest to governments that they have to follow the principles. We don't think that putting a law at the moment would make sense, because it would be extremely difficult to apply it because the science is still evolving. So that's the answer at the moment, we hope. But still, we will be working on delivering recommendations to government in order for them to know how to deal with these matters, let's say. But regulation, I say it's a bit too much for the moment. We have some regulations already existing, like the GDPR for the data, and this is already very good. You also have to understand that this depends, and this was also a question raised by the European Commission. It depends on the criticity of the thing that you are working on. Let's say there are some, if you work on a non-critical system, such as, let's say, an AI which is telling you what is the movie that you're going to watch next, then it can do wrong, no problem. You don't like the recommendation, you just watch another movie. So there's no need to regulate anything here. But if it's about driving a car, or monitoring a nuclear power plant, or deciding if you have cancer or not, or deciding if you have a loan or not, then it's a critical system. Then it needs maybe to be taken with much more precaution.
We have a question which is linked. Should we apply regulation because of ethical issues? But
I just answered that. I say we take a lot of care of ethical issues. And we are not the only ones. If you go on the web, you will find there's a Chinese guy, I can't tell you his name, but who has looked at all the ethics documents published at all the organizations and on all the matters. And there's a website which presents, let's say, something like 80 existing documents about the ethics of AI, which are very similar, but not always. So we are working a lot of people are working on ethics. But once more, regulation is a bit too strong for the moment.
We have a question from Benoît Leblanc, who was our former speaker last week. Thank you, Benoît, for being here. So how can you make a difference between AA results and efficient computer programs results?
Okay. They can be compared. It can be compared. If you look at the image processing example, you can look at the quality level, the error rate from deep learning system and from, let's say, traditional computer vision system. So if you look at the output is the same. It's a class. So a traditional computer vision program will give you an output class, and an AI system will give you an output class. the way that it's doing is quite different, but if you don't know that there's an AI inside, you probably will not notice the difference. Now, I know that, Benoit, since the question from Benoit, I know that Benoit is really a fan of symbolic reasoning and all these kind of things. And so now if you start trying to do reasoning with a system, if it's an AI system, it will probably behave very, very differently from a traditional program, although it can be faked. So so let's say that it's very difficult sometimes to tell the difference. The difference in the eye is in the eye of the developer.
There is a question linked to what you said before concerning recognition, image recognition. Mm-hmm. So do you know if it was drinking coffee as opposed to drinking other liquid, it was really difficult, or it's just recognizing the act of drinking itself?
I think, frankly, I don't know. I have to look at the data in more detail. My impression is that it's really distinguishing drinking coffee from all the other activities, and not only from drinking tea, because of course drinking coffee and drinking tea is very difficult. For example, you cannot tell if I'm drinking coffee or tea here. It's tea.
Concerning energy and material consumption, did you mean around the end of your talk that AI is going along a dead end and will be stopped more or less soon?
It's a part of the risk for an AI winter, because we cannot go this far. We are not going to go this way forever because of this famous doubling every 3.4 months. So we have to find other ways. So the dead end is that you are not going to put all the data of the world in the biggest machine that you can think of, and then be building an AI which is a general AI. That doesn't exist. Huh? So AI will be still able to do very specialized tasks, and for this you can be rather you can have some economies in terms of learning and data, etc. But in order to build a very, very big AI system with completely different competences, like we are ourselves, we need some other formalisms. We need to combine machine learning, which is very good at some specialized tasks, once again, processing speech, recognizing images, etc., with other things, as I was saying in the end, like knowledge and reasoning, and also modeling and simulation. So for me, the dead end is to do this hybrid AI, but we are not there yet. It will demand a lot of work. For example, in France, we have one of our 4 AI institutes in Toulouse, which is devoted only to looking at hybrid AI.
We have 2 questions who are kind of linked, so I'm going to read them both at the same time. So could quantum computing be a solution to the AI energy consumption issue in the future? And if yes, if so, by when? And the other one is the limit of AI only a limit of computing power? Meaning, do you think AI is ultimately limitless due to the Moore law?
Okay, so the first question, well, yes, I'm not a specialist in quantum computing, so I see what my colleagues are saying. Yeah? We have some quantum computing researchers at IBM. And so, yes, quantum computing, when it will happen, will be able to process much more efficiently the data. This is well known, so we will be able to reach orders of magnitude of efficiency with quantum computing. But when this will happen, no one knows. Personally, I think that it will take many years, more than 10 or 20 or 30 years, but I'm not the right expert to talk about it. But it's going to take a while because we are really at the very, very beginning. And the second question is it only a question of
computing power, the limit of AI?
No, it's not. At the moment, at the moment, people are really increasing the computer power, the machines, etc. But as I said, it will not go like this forever. So once again, it will be a question of combining these systems with other kinds of activities. If you listen to the big leaders of AI, to Yoshua Bengio, for example, and Yann Lequin, who won the Turing Prize last year for their work on machine learning, on deep learning, together with Geoffrey Hinton. So there were 3 winners of the Turing Prize. If you listen to them, and I attended a few talks by Yoshua recently, and they all start to talk about the work of Kahneman about system 1 and system 2. So I'm going to say a few words about that. So Kahneman is a Nobel Prize in economy. He's also who has worked on how our brain works. And his theory, which is expressed in a book which is called How Thinking Big and Small, something like that. You know, yes, or Thinking Fast and Slow, is that we have two main processes in our brain, and I think that even Benoit talked very quickly about it last week. So system one is how we process the data very quickly. So I see you on the screen, Martial. I know that it's you. I don't need to reason. Or you're telling me 2 times 4. I know that it's 8. I don't have to think about it. But if you ask me 235 times 692, then I have no immediate answer. I have to think about it. I have to reason. And this is a slower process. So it's another part of our brain. It's system 2. So this is just immediate examples. Huh? And so the theory is that we are always interlinking these two ways of thinking. The fast system one, which is able to identify objects, animals, do quick reasoning, recognizing people, making many decisions immediately, and the slow system two thinking, which needs reasoning, and they are always interacting. And so this is what now Yoshia Benjo and even Yann Lequin are saying for what could be the solution for building AI, which is more efficient and more powerful. And there's more subtlety in here, but I will stop there.
Could the decision-making thinking logics of AI algorithm could be counterproductive in some cases? Could it be victim of cognition and/or cultural boundaries?
I'm not sure. Can you say it again, please? Because I'm not sure I understood the question.
Could the decision-making thinking logics of AI algorithms be counterproductive in some cases?
Yes.
Could it be victim of cognition or cultural boundaries?
I don't know what you talk about for what you're thinking of for cognition or control boundaries, but yes, it can be counterproductive. We have seen examples of AI systems which behave well because they were trained bad. And so, I mean, it's like many technologies. They can be used for the good, they can be used for the bad, they can be badly used also. What did I want to say? So I will come back to it later. Maybe I had another thing to say, but I need to think about it a bit more.
Why some AI become racist, like the one from MIT or the chatbot from Microsoft?
Yes, because, this is what I wanted to say. And it helps me recovering what I wanted to say before. So it depends on the data. If you put racist data in a system, it will learn the racist behavior. That's just how it works. So that's a very important point. Maybe I haven't insisted on that in my talk, is that the main hypothesis with machine learning is that the present and the future are like the past. Because you learn from the data that you have, and the data comes from the past. So what you learn is really how the systems have been behaving until today. But if the present or the future are very different from the past, let's say, for example, when we are in a COVID crisis, as we have been in the last 3 months, the reasoning are completely different. The way people react, the way the industry is functioning, the way we are linking to one another are completely different. So things that we have learned from the past cannot be used in this new context. So this is really how things can go wrong. And then leads me to go back to this question of causality. Because causality is really, if you work on causality rather than correlation, then you don't only learn from the past, you learn about how the systems really work. And so it's much more efficient. But as I said, it's much more difficult.
How long do you think it will take AI to be able to recognize every human action?
Forever. Forever. I don't think that it will be able to do that. As I said, you cannot put all the data of the world in a big computer and do a general AI. At the moment, we don't even know how we do it. So, and it cannot be put in machines. So yes, people talk about super intelligence, and that is going to be be able to do more than when we do. For the moment, there's absolutely no sign that this can happen in any foreseeable future.
It's more like asking you for a reflection than a real question, but can you speculate about strong AI and specifically about consciousness?
No. You have to ask really philosopher to talk about that. For the moment, let's say this machine. I don't know. I don't even know what is my consciousness. So I have difficulty to talk about consciousness of a machine. So for the moment, it's very. I think maybe the consciousness is also in the eye of who is observing.
Do you think that as AI will probably take the jobs of a lot of people, we should rethink the economical model linked to AI and rethink the place of work in the society?
This is what we are doing, in fact, because as I said, in the global partnership on artificial intelligence with these 15 countries involved, we have four groups, well, 5 in fact. We have 5 groups of 20 to 30 experts, and one of them is looking at the future of work with AI. So we know that the work is going to change because AI will be able to do a lot of specialized tasks that we are doing at the moment, but the jobs probably what we know more or less is that the jobs will stay, but the tasks will change. But the job consists of many tasks. Even you can talk about, let's say, replacing a truck driver by a machine. But the truck driver, okay, he drives his truck, or he or she, but he also gives the bill to the customer. He also talks to gets the material out of the truck, etc. He's doing many different things. And so we are not going to have a robot truck driver, for example, not for the moment. So the task of a truck driver might change because when the machine will be able to drive for him for a long period, but there will be still monitoring activities, there will still be other activities. So once again, we think that the jobs will stay, most of the jobs will stay, but that the tasks will change. If you can read a book which is very interesting about health. It's I have to remember the name of the author. Eric, what's his name? Eric. Sorry, I have to look back in my data. Deep Medicine. That's the title of the book. It's something like a 600-page book about all the applications of machine learning for medicine, and it's a very interesting book because it shows really dozens of examples in all the activities of health, whatever activity. But the main argument of this book is that machines will be able to process the data and facilitate the work of the doctor, of the assistant, or whatever, facilitate the work. And with this, he will have more time to spend with the patient. And this is really an important task in a doctor's activity, is to understand the situation of the patient. It's not only looking at data, it's really a lot of exchanges. So the very optimistic message of this book is that the machine will help us to be more efficient in our work and to be more human in our work, which is really what we like, instead of processing data, let's say.
Someone from the chat, and I also,
sorry.
Someone in the chat also told the name Eric Topol.
Yes.
We have one more question. Do you think AI robots will integrate houses, and when?
But you already have robots in houses. You have the Roomba vacuum cleaners who have been in operation for 10, 20, 15 years already. So maybe you are not thinking of this kind of robots. You're thinking maybe of robots who are able to help, especially elderly people. So there are prototypes, and this is what people are working on. There are some small robot animals that can also, let's say, secure elderly people and exchange with them. So yes, there will be robots in houses for sure, but they will not be general AI robots. They will do specialized tasks. In fact, if you take the white book, the AI white book that I coordinated for INRIA 4 years ago. The first example is a house robot. And at the moment, we are finalizing the 2020 edition of this white book, and we start again with the same example of a home robot.
So we have one last question from the Q&A, but I think you already answered this question, and so then I will have my question. But just to be sure, I'm reading the question from the Q&A. Does quantum computing will change the limit of AI? But I think you already talked about it.
Yes, we talked about that already.
So my question is, your colleague, Luc Julia, who works for Samsung now, wrote a book saying that artificial intelligence does not exist.
Yes.
What is your point on it?
Yes, I know Luc quite well. I know his book. I know what he's saying. In fact, we are saying the same thing. We are saying the same thing. So that's a nice title for a book. It's a nice title because I think that it says much more than with another title. But what Luc Julia is saying is that we don't have general AI, for sure. So general AI doesn't exist. And this is also what I'm saying. We have specialized AI. And so, and then all the rest. So I agree with Luc, the general AI doesn't exist. So, but I think it's more efficient not to put general in the title of the book, and you have more space.
Thank you very much. Could you go back on your PowerPoint and put the last slide? Because since we don't have any more questions, I would like to first thank you very much, everyone, for following this presentation. That's fine. I'd like to thank you, Bertrand, for being with us tonight. Today was a big day for you with the launch of your group of experts on artificial intelligence. So we really appreciate that you took the time to be here with us tonight. So that was our second online conference on artificial intelligence. And our next event will be dedicated to French and Israeli vision on artificial intelligence. And for this conference, we will have the chance to have with us as a speaker, Cédric Villani, who is a mathematician, is a Fields Medal laureate, member of the French Parliament, and he played a leading role in establishing France's AI strategy. So this event will happen in September. And for more information about this event, the date, and to register, you can go on our website, ai-n-ethic.com, which we created this website specifically for this series of conferences and debates. So you can subscribe there and we'll keep you updated. And you will also find on this website the videos of today, the video of last presentation last week, and more resources that we are going to put there very soon to learn more about AI. So once again, thank you very much. Go subscribe on our website and we'll keep you updated. And once again, thank you very much, Bertrand, for your time. It was very interesting. Thank you very much. Thank you very much. Bye.
Bye.